Okay. Um, okay. Thanks for the introduction, Matt. So I guess we'll start with this thesis defense, which I've been quite nervous about since yesterday. Um, so yeah, I'd like to tell you what I've been working on for the last 6 years. Cool. So the title of my thesis is Expanding the Reach of Quantum Enhanced Gravitational Wave Detectors. It's a lot of words, so I'll try to break them down slowly as I go through the talk. But I think the gist of it is we have detectors that detect gravitational waves. Somehow quantum mechanics makes them better. And there was a point where I tried to make even that better, and I think it worked. So I'm going to tell you the story. Um, so starting at the beginning with Einstein's theory of gravity, um, this theory can be summed up in this quote that I'm sure a lot of you must have seen many, many times, and you're probably pretty sick of now. But it says, space-time tells matter how to move, and matter tells space-time how to curve. The meaning of this is basically that uh, any uh, so any object that has mass, it'll like bend space around it. And the space that is curved and bent around it will sort of dictate how things move in that space. So this smaller body orbiting this big body is basically because of the dent that this has created in space-time. So um, one thing that comes out of this theory is the idea of gravitational waves, which are these disturbances in space-time that propagate outwards from any asymmetric source. Um, for them to be measurable, for them to be significant, we usually are interested in ones that come from very extreme mass events. So, for example, this is two black holes that are colliding with each other, and you see as they merge, they kind of let out these ripples. Um, Eventually, these ripples reach Earth, where this is vastly exaggerated thing, but they stretch and squeeze space as they pass by Earth. And yeah, and this is what we have been measuring since 2016. So how do we actually measure this? Um, we use something called interferometry, where we have this laser beam that's shot through this beam splitter. It's split in two, and those two parts come back are reflected of two mirrors, and they recombine with this beam splitter again. And based on how much the difference in their paths is, that decides whether they add up or they subtract. And this is called interference. So um, once a gravitational wave passes through, it'll change this relative length because it's changing space. It's elongating one arm while shortening the other arm. And that will change the amount of power that comes out of what we call the anti-symmetric port. And the reason, and this is basically how we can detect any length fluctuation. So if a gravitational wave comes through and it comes and stretches and squeezes space, this is how we hope to measure it, by seeing how much power is coming out on the detection port. So we have two gravitational wave detectors in the US, the two LIGO detectors. We have LIGO Hanford in Eastern Washington, in the desert. We have LIGO Livingston in the swamp in Louisiana. Um, this is right next to a currently decommissioned nuclear site where they were enriching plutonium for the Manhattan Project. So there's history to that place. Unfortunately, I don't have anything as glamorous to say about Livingston. Uh, there's a lot of logging that happens over here. So these two detectors are part of a much larger detector network. Well, not much larger, there are like a few detectors more. But there's a 3 kilometer detector in Italy, Virgo. Oh, I should mention, these detectors have 4 kilometer arms, so it's quite long. There's a 3 kilometer detector in Italy called Virgo. There's a cryogenic detector inside a mountain in Japan called Kagra. There's a prototype detector in Hanover in Germany called Geo. And very recently, LEGO India has gotten full approval. So maybe in the next 5, 10, 15 years, we'll see a LEGO India pop up, hopefully. Uh, okay, so what does this gravitational wave signal look like? So this was the first gravitational wave signal that was measured by the LEGO detectors, which came from a pair of black holes. This just shows the space being like stretched and squeezed, and this goes up in magnitude until the black holes merge and then goes back down again. The thing to pay attention to here is that this number of strain, so strain is the relative length change that is induced by the gravitational wave. It's very, very small. It's like 10 to the minus 21. So we have these like extremely massive objects, which are as heavier than the sun, way heavier than the sun, actually, creating very, very small signals. And how small are these signals actually? This video can give some context. Um, I forgot to enable this. Sorry. Okay, I'm going to skip this. It's a cool video. It's a cool video, but basically, uh, the amount that it actually moves, stretches, and squeezes space, a gravitational wave uh, that reaches Earth from these black holes, and the length we're trying to measure is a thousandth of a proton. It's much, much smaller than most things we can imagine. So let me take a little detour and ask a very basic question. Why is it hard to measure small things? Like, we take it for granted that it is very hard to measure small things, but why is it hard to measure small things? And I'll give an analogy over here. Imagine you're sitting in the back of an airplane and you're trying to hear someone's heartbeat from the other side of the plane. It's impossible, right? And why is it impossible? Even if you had the most sensitive hearing ever, it would be impossible, not impossible, but it would be really hard because of noise. There's noise everywhere. Just like in an airplane, there's a lot of sources of noise. There's people talking, there's people walking, there's the extremely loud engines of the airplane. Similarly, when we're looking for gravitational waves and gravitational wave detectors, we have a lot of noise, a lot of different sources of noise. So this is what we call a noise curve. Again, so this quantity on the y-axis is strain, this relative change in length. And what this plot basically tells us is that at every frequency, how much noise should we expect to see in the detector? So this x-axis is frequency over here. We see that the detector is kind of sensitive, most sensitive around this 100 hertz-ish area. The only thing to know about this plot is that more noise is bad, less noise is good. And because my thesis title has quantum in it, I am going to very conveniently ignore all the noises that are not quantum. So, okay, so let's talk a little bit about quantum noise then. So what is quantum noise? Like, what is this quantum vacuum noise? And I'm sorry, but the not physicists in this room will just have to trust me over here. There are quantum fluctuations in space everywhere. We can't wish them away. This is just physics happening. So these fluctuations, they end up entering the detector, and then they go and turn into this kind of fuzz. So that clean picture of waves adding and subtracting that we had in that interferometry video, it's not actually that clean because there is this fuzz ends up being this fuzz on the wave. So we have these fuzzy waves. Fuzz from both arms adds up, creates more fuzz, and this is what is quantum noise, unfortunately. Yeah, so going back to a picture of quantum noise, conceptually, we can divide it into two major parts. There is shot noise and there is radiation pressure noise. And before I describe what these noises are, I'm just going to mention very briefly that for a wave at a given frequency, there are two things that we care about a lot. We care about the amplitude of the wave, which is how big the wave is, and we care about the phase, which is where the wave is. And why is this important? Because both these things for this fuzzy wave, have noise, have uncertainty, and this uncertainty translates into the quantum noise that we see on the detector. So this phase uncertainty, the uncertainty about where the wave actually is, that translates into shot noise. And in the photon picture, we can think of it as the detector that we're using to measure the gravitational waves sees some sort of randomness in the photon arrival times. So this is called shot noise. This goes down with increasing optical power. One way to think about it is if we have more photons, we're sending in more information. So we're kind of reducing the statistical uncertainty. Um, then we have radiation pressure noise at low frequencies, which comes from the uncertainty in amplitude. Now, radiation pressure is basically the force exerted by light on any object. And because LIGO's mirrors are suspended on pendulums, every photon has a small amount of source of force that is exerting on the mirror. And because there's a lot of photons, there's a lot of light in the interferometer. The noise in this force actually turns into actual noise on the mirror motion. And this is what we call quantum radiation pressure noise. And unlike the shot noise, instead of going down with optical power, this goes up. So we've already run into this kind of trade-off situation where we can only make one noise better by increasing the power, but we'll end up making the other noise worse. And this gives rise to the idea of what we call the standard quantum limit, which we see that as we increase power, we're seeing the shot noise go down, but we're seeing the radiation pressure noise go up. And this noise curve can never exceed the standard quantum limit by just if we just manipulate power. So before I talk about how we start getting around these problems, I'm going to introduce everyone to the idea of quantum squeezing. So this is Lee McCullough. He was a research scientist here, is now faculty at Caltech. He was one of the biggest driving forces behind the project that would eventually become my PhD thesis. And this is him explaining quantum squeezing in a nice YouTube video that went along with the press release for our last paper. So yeah, now this wave that I showed you with fuzz, with uniform fuzz, it's called a coherent state. And this is what a laser outputs by default. Now, we can think of this coherent state as having equal uncertainty in amplitude and phase in some units. If we look at it, like I can represent this thing as a circle over here, like the uncertainty over here is equal to the uncertainty over here. And what I can do, what quantum mechanics allows me to do is it allows me to pinch one of these uncertainties at the cost of increasing the other one. So I can say squeeze amplitude. So you see over here, the amplitude is more certain, but we have more uncertainty in phase. That obviously affects the noise in the interferometer. The radiation pressure noise goes down, but the shot noise goes up. Similarly, you could squeeze phase, and then the shot noise goes down, but the radiation pressure noise goes up. And it's worth noting here that I can represent these squeeze states by this ellipse over here that was that circle that I just took and squished. And this ellipse going from like phase to amplitude squeezing is pretty much just rotating. So conceptually, that's pretty useful for us because we like to describe this as a squeezing rotation when squeezing is changing from one type to another type. And it's also worth pointing out that these are not the only two possible squeezings you can do. You can rotate to anything between amplitude and phase, but that's a little involved, so I'm going to stay away from that for now. But as some of you must have seen, this leads to the same trade-off that we were seeing before. Even if we put in squeeze light, we do amplitude squeezing or phase squeezing, we end up making one noise better, but the other noise worse. We're still kind of hurt by the standard quantum limit. So the solution to this is actually, if we look at this very carefully, there's nothing that tells us that, we have to be squeezing the same way in every frequency. So ideally what we'd want is that because we see the shot noise is better when you phase squeeze and radiation pressure noise is better when you amplitude squeeze, the thing we probably want to do is try and phase squeeze at high frequencies while turning or squeezing into amplitude squeezing at low frequencies. And this is what my PhD has been about. It's what we call frequency dependent squeezing, where we do phase squeezing at high frequencies and radiation pressure squeezing, amplitude squeezing at low frequencies. Um, and in principle, we should win broadband. Yep. So what does frequency dependent squeezing look like? So this is a brief optical layout. I'm not actually going to go into the details of this. This has three major parts. We have to first make the squeezing. We have to rotate it at low frequencies. Remember, I said rotation is going from phase to amplitude. And then we have to inject it, which means just put it in the interferometer. So when I started my PhD in 2018, two of these were solved problems. One of them was not. Um, and I'm happy to say, as of today, the third one is also a solved problem. And because it's my defense, I'm going to take some credit for that. But before I tell everyone how it works, I'm going to briefly introduce people to the idea of how we actually make squeezing. And now the simple version of this is we have something called a squeezer, convenient, right? So it's a nonlinear crystal. This is the crystal. It's a very small crystal that goes into what we call an optical cavity, which is just a bunch of mirrors. And this creates something called squeezed vacuum. This whole system is called an optical parametric oscillator, or OPO. I'll be using that term later, so that's why I'm mentioning it now. The squeeze vacuum, when we inject it into the interferometer, it's what creates these like phase squeezed or amplitude squeeze states. So now I am going to give a warning over here. I'm going to get slightly technical because I'm going to try and explain how squeezing is actually created. But feel free to tune out because it's not going to impact the flow of the presentation, hopefully. And I'll give everyone all clear. So now I'm going to talk about the sideband picture of quantum noise. Yeah, I have these orange slides to like indicate slightly technical slides. So the sideband picture of quantum noise basically says that this wave with some uniform fuzz, you can think of it as some field at some frequency, which we call the carrier, which is the frequency of, what we think is the frequency of this wave. But it's also surrounded by a lot of other small fields at every frequency around it. And what makes this fuzz uniform is the fact that all of these fields, which we call sidebands, are all at random phases with respect to each other, and we call them uncorrelated. And these are what end up masking the gravitational wave signal. These are what end up showing up as noise. Now, what squeezing does is squeezing takes these uncorrelated sidebands and just turns them into correlated. So for a given frequency above and below the carrier, what I'm doing is I'm creating a more definite phase relation between the upper, what we call the upper and lower sideband of the carrier. And the squeeze angle, which talks about how if we're squeezing amplitude or phase or anything in between, this depends on how we correlate these sidebands. And to explain what I mean by this, I'm going to start with an analogy. Consider two coins, and say you give heads a value of -1, you give tails a value of +1, and you toss them both like 100 times. So if they're uncorrelated, if if they didn't have anything to do with each other, then we'd see that both of them individually, as you expect, would be 50% heads, 50% tails, but the sum and difference would have the same statistics because they'd be the same as much as they're different. So the sum would be 0, 50% of the time, the difference would be 0, 50% of the time, and their variance around it would also be equal. Now, on the other hand, if I was to say correlate these photons, and I say these coins and say that I want them to be same like 70% of the time. Now, what I see here is that because they're same more often than they're different, the difference is going to be 0 more often. But their sum is actually going to have larger variance. It's going to be plus or -2 more often. So what I'm doing is by introducing these correlations, I'm trading off between the statistics of these two metrics that I care about. I can change this correlation. I can say that, okay, now I want them to be opposite 70% of the time. And now what I see is that I've switched the distribution in sum and difference. So what I've done essentially is I've created a squeeze state in these coins. And it's a very crude analogy, but basically the individual coins correspond to the sidebands in the sideband picture, and the sum and difference correspond to the amplitude and phase metrics, which we call quadratures. It is a crude analogy, but the math is actually pretty similar. There's a sum involved, there's a difference involved. And the takeaway over here is that correlations between sidebands decrease variance in one quadrature while increasing variance in the orthogonal quadrature. Um, so what is our magic crystal doing? It's basically taking one photon, which is at twice the frequency of the carrier. It's breaking it into two photons, one above the carrier and one below the carrier. And these photons are entangled. They're, I don't know if quantumly is a word, but they're quantum entangled. And what this is essentially doing is turning these previously uncorrelated sidebands into correlated sidebands. And this is how we produce squeezing from these crystals. And now to increase squeezing, we put it into an optical cavity. An optical cavity is just a system of like various mirrors together. So this is two mirrors. And we have for a certain range of frequencies, which we call the bandwidth of the cavity, it amplifies the optical power inside the cavity. So we just use that to our advantage to like use not that much light to produce a lot of squeezing, because we don't care about having squeezing at all frequencies. We only care about squeezing within our bandwidth. So we can trade off a lot of bandwidth for a lot of power. Yeah, so this ends this section. This is the all clear. The second part is, well, now that we've made squeezing, we need to rotate squeezing. And so how do we rotate squeezing? So we rotate squeezing with a phase shift. But the issue here is that if I was to just simply phase shift any beam, it would affect all frequencies in the same way, and that would just turn phase squeezing to amplitude squeezing. But what I want is a frequency dependent phase shift. I want something that leaves the phase squeezing alone at high frequencies while turning it into amplitude squeezing at low frequencies. So this can be done with an optical filter cavity, which is again cavity, two mirrors. And this is something that will produce frequency dependent phase shift. Again, little math, but this is going to be faster. Basically, if we have a perfectly reflective end mirror, then the field going out of the optical cavity is related to the field going into the optical cavity with their ratio is just a frequency dependent phase shift. So within the bandwidth of the cavity, this beam just sees the phase shift. And what this leads to for squeezing is this is how we can rotate squeezing at a given set of frequencies. In the sideband picture, it would look like this. We have some sort of squeeze state, and then we have the cavity that's flipping some of these sidebands because it has a phase response. So now we see at low frequencies, we have a different correlation than we do at high frequencies. And this is pretty much the principle of how frequency dependent squeezing works. Okay, so we've got making squeezing covered, we've got rotating squeezing covered. Now, let me talk a little bit about injecting squeezing. And when I say little, I mean very, very little, because it's a very trivial, conceptually it's very trivial. You just put it into the interferometer, but it's quite hard in practice. And I think it's beyond the scope of like general interest. But if people have questions, I'd be more than happy to answer them later. Okay, so this ends like the background that I need to get for this talk. So let me move on to the more fun part, which is, well, the story of what we actually did. So when I started here in 2018, I started working on the frequency dependent squeezing prototype at MIT. And as Matt mentioned in his introduction, this involved a 16-meter filter cavity, which is in a lab here at NW17. This is a picture of our squeezer, our optical parametric oscillator in the vacuum chamber. This is me when I started, when I was a newbie. This is Chris, who has flown in from California today. He was a senior grad student on this project. So this photo was taken by Lee, the person who had introduced before. When we first stabilized this cavity in air, I did not know what was going on. I was very clueless about why there were photos being taken. I'm sure Chris knew what was happening. But yeah, that was kind of the start of the project, my time with the project. Now, let me give some context about what actually went into making this project work. Because at the end of the day, I have introduced a cavity as two mirrors. Like, how hard can two mirrors be? So another warning, This is not going to be technical, but there's some oversimplification and there's a lot of self-indulgence ahead. Um, so how much is a meter? Everyone probably has an idea of how much a meter is. It's about as much as a guitar. So how much is 16 meters? This is easy, 16 guitars. So how precise does the cavity length need to be usable? This is a pretty astounding number. If our length is more than 8 picometers away from optimal, the cavity is unusable. We can't stabilize it. We need it to be within this within this little window to be usable. And how much is the picometer? For reference, this is a little cartoon of a helium atom. It's about 60 picometers in diameter. 8 picometers is probably a tiny fraction of this. Finding this usable region is like finding a needle in a haystack. It literally is. We had one night, we had a script running all night, which just tried to look at camera pictures and see if we could see any cavity flashes. This was challenging. And once we find this usable area, we also need to keep it there, which is a pretty challenging controls problem. Now, admittedly, it's not as gargantuan as I'm making it sound, but to make it work, we need a lot of things. And this is a brief layout of what our optical system looks like. I'm not going to go into the details. I'm just going to say that to make a project like this work, we need a lot of in-air optics. We need in vacuum optics, that's me inside the vacuum chamber after like 1.5 hours. It starts out as claustrophobic and ends up becoming weirdly meditative. These are the electronics. This is all in our lab in NW17 over here on campus. So yeah, after a bunch of work, eventually in 2020, we had results that Matt mentioned. We were very happy with these results because this was the first time we ever saw frequency-dependent squeezing at gravitational wave frequencies. I'd like to point out the useful parts of this plot. So we can ignore all the curves except for the purple and blue ones. And basically, in our lab here, we don't have an interferometer. So we don't have radiation pressure noise. But we can still measure frequency-dependent squeezing by seeing how a filter cavity affects short noise and how squeezing affects short noise. So when we see phase squeezing, which is this purple trace, this will be below our unsqueezed short noise, and amplitude squeezing will increase short noise, so it'll be above our unsqueezed short noise. And as we come into the bandwidth of the cavity at these frequencies, we see the squeezing rotate. So now the phase squeezing turns into amplitude squeezing over here. So this is the purple trace, and this amplitude squeezing turns into phase squeezing. It doesn't go all the way in this experiment because there are other technical factors involved. There are optical losses. We end up losing a lot of squeezing in the cavity. But luckily, this was a prototype. Our actual cavity on site was much better, and I'll get to that in a bit. But yeah, once we spent a lot of time on this experiment, we decided that we should try to milk it for a few more results. So we have some other results from this 16-meter filter cavity. There's a special case which we call an amplitude filter cavity. I'm not going to go into too much detail, but this is just basically if instead of rotating, if we were to use the loss in the cavity to just eat all the squeezing up at low frequencies and get rid of all the excess radiation pressure noise. So this could be potentially useful if you have a very lossy cavity and you are constrained by, the technical aspects of your experiment. We did this cavity characterization using an auxiliary field. This plot is a little involved, so the only thing I'd want to point out to people here is a look at how good the data looks compared to the model. It looks very close, and it's something that we started using on site, and it was quite useful. So yeah, meanwhile, in LIGO, LIGO has started using squeezing during O3, which was the third gravitational wave observing run. And as we can see, the squeezing was not frequency dependent, it was frequency independent. So we saw short noise go down at high frequencies, but we saw radiation pressure noise go up at low frequencies. It's not as dramatic as I had shown in my earlier models because in an actual interferometer, there's a lot of other stuff going on at low frequencies. But we knew that eventually we were going to have a better interferometer and we were going to have more squeezing and we were going to have more power. So this would be a problem. And as I've been blabbing about, we have a solution to this frequency-dependent squeezing. So This brings me to the second part of the story of my PhD, which is exile. This is Dante in exile. Um, so yeah, this brings us to LIGO Hanford Observatory. Uh, and this was a photo that we took in February 2022, where I did not realize how cold it would be outside. Um, but yeah, so what did I go to Hanford to do? Now, luckily, I've already introduced you guys to the idea of a filter cavity. So I can just say we did the same thing, but longer. 300 meters to be precise. Now, how much is 300 meters? 300 guitars. There's a better reference I had. Think about Prudential, but a little bit longer. That's 300 meters. Now, I would like to mention over here that, like, in order to actually do an experiment like this in a 300-meter cavity, there's a lot of stuff that needs to be done before we can actually go into science. There's a whole bunch of infrastructure updates. And it wouldn't be fair if I didn't mention these because there's a lot of work that went into this, and a lot of people put a lot of work into actually getting the system ready for us to actually do science with it. So after the third observing run, a new 300-meter vacuum tube was installed and a new beam tube enclosure. Two new vacuum chambers were added to both sides because we had to move the squeezer to a new chamber because there were way more optics. Now with the filter cavity, we had to add two new optical tables. And this is a slide I've stolen from Vicky, from one of her talks, which shows the progress of this construction. And this, please keep in mind that this is coming out of COVID. So we were short on people. There were restrictions everywhere. And it's amazing that they managed to get this done in that time frame. But yeah, this is a whole beam enclosure that you need to construct to house this 300-meter tube to keep it away from the elements, away from tumbleweed, animals, all of that. Once the beam enclosure was constructed, it looked something like this. This is how it looked from the inside. This is before the filter cavity tube was installed. This is one of the vacuum chambers being moved to the end station that was created for the filter cavity end mirror. This is Mitch, one of the engineers on site, working on getting the filter cavity tube ready. And this is a nice video by Arnold, who is at Caltech now, but this is at LIGO Livingston, they were installing the seismic isolation in one of these chambers. This just goes to show how much infrastructure work this actually involves. It's quite impressive. But yeah, with all of this setup, our first task was to reboot the squeezer because the squeezer had moved to a different chamber. So this involved a bunch of work. I'm not going to go into the details of what we actually did because it's kind of boring, but I'll show you some nice pictures instead. This is that seismic isolation that I showed in that last video that was being installed. This is how the vacuum chamber looked from the inside. This is the squeezer source, the OPO. There's no way to make this look nice, by the way. It's any angle is just going to look like shiny metal. So this is, I think, the best picture I can produce. This is how the in-air optics look. This is actually from LIGO Livingston, but the lucky thing about having two sites that are supposed to be identical is that if I show a picture of one side, you can assume that the other side looks pretty similar. This is us replacing a very expensive and very fragile fiber one day. Basically on site, one of these fiber feed-throughs to this vacuum chamber had broken, and we had a spare at MIT, but just one spare for Hanford. And this was extremely fragile. So this is a 5-person job with 4 people feeding in the fiber and 1 person pulling it out, eventually turning into 1 person feeding the fiber and 4 people pulling it out. And we knew that if we went wrong at any point, it would be a 4-month wait before we could get anything new. So that was quite harrowing. This is the vacuum chamber with me for scale. It's very loud in these clean rooms, so we have to use walkie-talkies to talk to each other. Looks kind of cool. Feels also kind of cool. This is the relay tube between the squeezer and the interferometer. This is how the squeezing is put into the rest of the interferometer. So eventually, we did get squeezing back. Success. You can see that like short noise was reduced at high frequencies. And we also start seeing the effects of radiation pressure noise, which was a first for Hanford actually, because Livingston had seen it during the third observing run, but Hanford had not. And while we're doing this, the filter cavity is almost ready to use. So this is a picture of the 300-meter tube after it's been installed. This is the filter cavity end mirror. This is more tube because it's 300 meters. This is Now we just had one step left, which was opening this gate valve. There were four of them. And these gate valves, when they're open, they make sure that this whole thing is one big contiguous piece of vacuum. So this brings us to the day Matt talked about, November 18th, 2022, which just happened to be towards the end of this commissioning meeting that we had. So everyone just happened to be on site that day. It was a very interesting day because we had made this whole plan that, we'd take 1 week to try and align the cavity, 1 week to stabilize it. It's going to take 3 weeks for it to be done. How are we going to look for the beam? If we don't find it, here's a backup plan. Looking for the beam is hard because we're looking for something that essentially looks like this laser pointer at the end of a 300-meter tunnel, which is about this wide. Luckily, we have technology. And we had a lot of physicists too. Eventually, this thing that we thought was going to take 2 weeks took 6 hours. And in stark contrast to the photo where I did not know what was going on, this time I knew exactly what was going on. And I'm happy to say that like LIGO Livingston managed to achieve the same thing in the same day on the same time frame. So that was an extremely good day. One of the rare times that things take less time than we expect. And obviously that luck wasn't going to last forever. So we had a very frustrating month after that. I'm not going to go into the details of what made it frustrating. I just have some screenshots from our log posts, which mostly have like negative emotions. We're not able to use this. Many unsuccessful attempts. Turns out the model wasn't accurate. But eventually it did work. And we got frequency dependent squeezing. And the day we got it, I was so excited. I took a picture of the workstation monitor and I sent it to a little Slack group. But I sent it without any context. So Lisa's response is one of my favorite things. Add more words. And I'm happy to say that's exactly what I've been doing for the last 1.5 years. I've just been adding more words. But yeah, we wrote this log post. There are a lot of exclamation marks over here. I have not included them in the screenshot. There was a comment that said a very happy grad student. This is Daniel Sig, who's the commissioning coordinator on site, and he really has seen it all. So he's not fazed by most things. But this result was enough to get him to actually go and look at the screen. So I think that was one of our biggest achievements, is getting Daniel interested. After Daniel, this also caught the interest of a lot of other LIGO top brass. There was champagne. It was a good day all over. So yeah, without further ado, let me show you the actual results. So this is what frequency dependent squeezing in LIGO looks like. The idea is quite simple. Now that I've been showing you ellipses for a long time. This purple trace is frequency dependent squeezing, this green trace is frequency independent squeezing, and this black trace is no squeezing. So we see that frequency independent squeezing, it reduces shirt noise at high frequencies, it increases radiation pressure noise at low frequencies, and we have successfully rotated the squeezing into amplitude squeezing. So we've reduced noise everywhere. So what we were hoping to achieve is what we did achieve. Now, some of you might have noticed that I've very conveniently not mentioned gravitational waves for like the last 40 minutes. So I should quickly talk about whether this actually helped LIGO. Yes, it did. So the way we measure how well LIGO is doing is by using this. One of the metrics we use is called the binary neutron star inspiral range, which if you have a system of binary neutron stars, there are two neutron stars spiraling into each other. This tells us how far into space we can see this sort of system to. And switching on frequency dependent squeezing boosts this range by about 20 to 30 megaparsecs. Now, how much is a megaparsec? It's a lot. It's about 40 times the size of the Milky Way. So we're like, frequency dependent squeezing is boosting our astrophysical range by like a factor of like, it's boosting it by like 20%, which is like 1,000 times the size of the Milky Way, which is pretty insane. So yeah, what does the future hold? Oh no, this highlighting is wrong. So yeah, first thing is we want more squeezing. Now we talk about how much squeezing we get in units of decibels. 10 decibels is a factor of 10. This is an exponential scale. 20 decibels is a factor of 100. We're kind of stuck at not sad, actually 5 is good. But we started at 3, we slowly started getting better throughout the run. In the future, we plan to get here, and something Vicky told me is that the difference between here and here is called job security. Uh, Unfortunately, not my job because I'm getting kicked out anyway. Uh, uh, but yeah, so this is something to look forward to. More squeezing. It's very hard, by the way, because we have to understand optical losses very well. There's a lot of people working on this right now. Um, there is a little project with it about alternate interferometer configurations. Now, this is slightly technical, so I'm not going to go over all of the details, but the fact is that if you take one of the cavities on the interferometer and if you detune it a little bit, you can create this high frequency dip that allows you to see neutron star physics that LIGO is not otherwise sensitive to. So that is something that requires us to rethink how we're putting in squeezing also just a little bit. Unfortunately, the paper we wrote says that this doesn't actually help us that much because um, what we don't know about the system is like our lack of knowledge of the system is pretty big right now. So we don't know where this dip would exactly be. And in all probability, we won't end up seeing any useful signals. Um, yeah. So this is one thing that, but there are other things adjacent to it in the future that people have been thinking about. One is like trying to increase the bandwidth of the detector and stuff like that. Um, one other thing is I didn't mention the standard quantum limit, and um, you all might have noticed that the standard quantum limit exists because we can't make one of these noises better at the cost of the other. Like we can't make both of these noises better together with these standard methods, but with frequency dependent squeezing, we can. So we can, in principle, break the standard quantum limit. So happy to say, not my story to tell right now, but stay tuned for Wen's paper and Wen's PhD defense. This has just gone up on the archive. LIGO does operate with quantum noise below the standard quantum limit. Um, yeah, so that's about it. So in conclusion, quantum noise dominates a large portion of the signal band in gravitational wave interferometers. Changing the optical power and injecting frequency independent squeezing leads to a trade-off between the low and high frequency noise, which we have solved by using frequency dependent squeezing. And I think I'm doing well on time, so I'm going to move to my acknowledgements. Um, so I would like to thank my advisor, Matt, and my committee for making this defense happen. One thing that I'd like to mention that this experiment is literally $1 billion experiment. So somebody has to front the $1 billion. So the National Science Foundation, without the NSF and without your taxpayer money, I wouldn't be able to do any of this. I have been extremely privileged to work with one of the best teams, I think, that exists. This is the squeezing team. I've been so lucky to find a set of amazing mentors. There's Lee, Lisa, Matt, Danielle, Sheila. Again, the highlighting is wrong. That's just sad. Um, and also, apart from the mentors I had, there were a lot of people who gave me company in the lab, who made this experience actually fun. Chris and Kentaro worked with me on the filter cavity in here. On site, we had Naoki, Camilla, and Natsuni, and Vicky has been working with me on both projects for a long time. I'm also extremely privileged to be a part of LIGO MIT. It really is one of the best groups that someone can ask for. It's I've actually come to see it as a sort of family now. So I'll be very sad to leave. My friends both here and in Hanford have been a source of support. They have made a lot of this worthwhile. And of course, my family, my parents and my brother, who have been a source of unconditional support since forever. And I would like to mention that having a family halfway across the world is hard. But what made things better for me is that I actually have other family here who have made me feel home over here. I have uncles, aunts, and some of them have come in for my defense today. So yeah, I've been quite privileged to have the people that I have around me. So yeah, back to conclusions and
We have a few minutes for questions. Anyone like to ask anything?
You showed the standard quantum limit. Is that a fundamental limit or is it like not?
No, so I can tell you where it comes from. Basically, the idea is that when you're making a continuous quantum measurement of something, you're kind of measuring, like if you're measuring the position continuously, you're kind of measuring its derivative too. So you can't measure both of them arbitrarily precisely because Heisenberg won't allow you to. So it leads to back action in the system. So in our system, this back action is radiation pressure noise. The standard quantum limit comes up when these are uncorrelated with each other. But if you introduce correlations, which is what we do with frequency dependent squeezing, then we can beat the standard quantum limit. We have something that gives us something called a quantum non-demolition measurement, or QND. Yep. So it's not standard. It is a limit. It is, someone has called it some quantum limit, SQL, but yeah. But yeah, keep your eyes peeled for Wen's paper, which is already on the archive. So
Other questions?
Sorry, go ahead.
No, please.
Super cool talk. As a biologist and not a physicist, this might be stupid. But you have two ways, right? So you have squeezing that can reduce one of the noises. And you could also just like up or lower the power of the beam to reduce the other noise. Is that also something that runs into the standard quantum limit, or is that something?
yeah, both of them. So that's when I introduced the standard quantum limit. Frequency independent squeezing and changing the optical power are both kind of intrinsically linked to the standard quantum limit. Let me see. Yeah, so this is a plot where we're changing the power over here. And we're like, this is where we're again, like sort of. Now, the way to actually like change this, there's another way to change this without doing any fancy quantum stuff. Is actually make our mirrors heavier. And then we can beat this limit. But the standard quantum limit is actually not defined as a universal thing. It's defined for the system. So the system standard quantum limit will go down if we increase the mass of the mirrors. It's an interesting point over there. It's actually turns out it's cheaper to do this weird quantum stuff than increase the mass and increase laser power. It's a cool quantum experiment, but we're doing this to find gravitational waves, and we wouldn't do it if it wasn't the most cost-effective method. It just so happens that there is this quantum thing, and I got a PhD out of it. So
It's also good to have cool things.
yeah, it's nice to have nice things.
Just make it bigger.
Yeah.
Sometimes it's technically hard, but also kind of sad. That's the best hand that we got. Other questions, please?
Well, I was about to ask, if you were not about to leave, what is the next thing you would do to make the system better?
Oh, good question. I would start working with Vicky on this modeling stuff and figuring out what our losses look like actually. That's one thing. I mean, if I were to keep working on squeezing, that's a big if. So yeah, this is an old slide, but this kind of it's like a brief budget of what our losses look like. But a lot of our unknown losses actually come from the fact that our optical modes are not matched well between different parts of the cavity. And actually trying to measure what that is a very, very hard project. And that's what a lot of people are actually looking into the actual quantum noise itself and trying to model out what these effects should look like. We have active optics. We have mirrors that we can change the radius of curvature of actively. So there is an optimum somewhere that we can hunt for. It's just kind of hard. So that's one thing. There is loss in the crystal itself, which we think we've managed to work around a little bit by changing the crystal position. There are a few things. I think it's not unreasonable that we see 6 dBs at Hanford in the next few months, but a lot of it depends on the interferometer. So if I were to keep working on it, I would spend more time thinking about the interferometer rather than the squeezer.
Other questions?
In the last, we were talking about the advantage of doing frequency dependent squeezing that can improve the critical binary range by 20 to 30 megapascal.
Yep.
To my understanding, the binary neutron star signals are sitting at the high end of the LIGO bandwidth, but you are increasing the signal to noise ratio at the low end. Then
So, I mean, the inspiral range is integrated over a lot of frequencies. It's not just at high frequencies. By the time you actually reach higher frequencies, you're looking at later points in the merger. You're looking at the, you're actually getting into points where you're not sensitive about, like the post merger and all. A lot of the signal actually does come from, like, a lot of the binary neutron star range comes from this, like, I would say 60 to 200 hertz band, and frequency dependent squeezing actually makes a pretty big difference there. There are plots which like have a range going up as a function of frequency just integrated. I don't have any of them in my talk, but they are pretty informative as to how like low frequency, it's not super low frequency. We're not looking at like 10 or 20 hertz, like, anything between like 60 and 200 is helping a binary neutron star range a lot.
I can say quantitatively that the integrand has the f to the 7/3 or minus 7/3. So it's always weighting higher to lower frequencies. Other questions?
Can you turn a squeezing angle wide?
Yeah. To everything between phase and amplitude. Just phase, amplitude, and everything in between. And if it wasn't frowned upon, I could like do it right now. But we're in an observing run right now. So
Let me ask a slightly harder version.
Yeah.
Of the question. So I think that answer was you can rotate the phase, let's say, at one particular frequency depending on what you want. How hard is it to change the frequency at which you get the frequency dependence?
a little harder because that depends on where the cavity is. That depends on where where the cavity is resonances. And now the one thing we can change about the cavity is we can change where its resonances, but we can't change its bandwidth with time. So we can rotate squeezing, at frequencies that we would want to rotate it at, but we can't rotate it over a larger range. That's harder. We'd have to redesign a cavity for that. I'm trying to see if we have any plot of a kilohertz. Yeah, okay. Yeah, like sorry. Yeah, here. So here we're doing this frequency rotation, like the squeezing rotation at a kilohertz. So we can do this at a kilohertz too. But the bandwidth of this rotation is going to stay the same as it does as what we do at low frequencies.
Other questions?
I think I have maybe two related and badly formulated questions. The first is like very similar to the one that was just asked, which is, it seems like just thinking for as long as it's Detectors, there are like sort of three things you might care about. There's how far away something's happening, what is happening, and when during that event, if there's something takes some time. So are you looking at like early stages or late stages of submersion, for instance? Yeah. And so one question is, it seems that what you're doing, you win on all of those. So, for instance, the lower your noise, then you can, for example, see the same event out to further, or you can see an event perhaps higher frequency or lower frequency. You can see an event with smaller amounts. How you view that sort of interplay between those three, or am I missing, say, a fourth? Sorry, maybe I can just ask the second question. Yeah, so yeah. You mentioned at the end, how does this really help? And you talked about like the range, I forgot what the name was, but essentially the range out to which you can. Yeah. My question as an experimentalist is, how do you know that's working? Like, how do you do ranging? So you turn on your detector with this frequency dependent squeezing. What is your verification that, cool, we have now increased the range out to which we can see mergers by such and such? That's a good question. And to my best knowledge, it's not something we've verified, because the way we calculate the ranges, we have a template for what the signal is supposed to look like. And we know what our noise is. So we just integrate, we use this as the integrand. And we say that if there were to be a signal over there, unfortunately, even though this number is huge, right, 130 megaparsecs, turns out there are almost no binary neutron stars colliding within that. We got very lucky when we saw the first binary neutron star collision. In 04, we haven't seen a single one yet. The moment we see one, we'll be able to tell where it is, and we'll be like, okay, we can see something at whatever direction or whatever distance. But one thing that, like, again, the range, the way it changes is very different. It's very dependent on what the event is, depends on what the mass is of the event. But I can say for sure that, like, with this frequency dependent squeezing, our rate of event detection of just binary black holes has gone up significantly. So there has been a significant improvement in LIGO's performance. If the absolute metric
of LEGO's performance that you're looking at is how much science comes out of LEGO. There's a lot of science coming out of LEGO because we're seeing more binary black holes now than we were before. What science is useful is a more subjective question. I think so that's why there's a lot of debates that go into, what we want future detectors to look like, and people are interested in different kinds of science, and that will inform how you design the detector. For example, if we were to keep working on our lower frequency, which is what a lot of future detectors plan to do, is be able to start seeing intermediate mass black holes that exist beyond the upper mass gap, which is a theoretical mass gap that says that you can't actually have supernovae that produce a black hole with mass above, I think, somewhere close to 100 solar masses. So that tells us about bigger black holes and how, once we learn about the populations, we learn about where they came from. It tells us a lot about how these black holes came to be, which is a big open question right now. On the other hand, there are people who like to think about neutron star physics and I would think of myself as one of them. Black holes are cool, but for me, they're kind of boring because they have three things. On the other hand, neutron stars are completely unknown quantities. So if we could have a detector that's looking at the post-merger signal from a neutron star, that'd be amazing because we'd actually see what comes out. That is something we're not able to do right now. We can't do, even if we have a lot of frequency dependent squeezing, we're not going to actually hit that target. Because as you see, the sensitivity at a kilohertz is a lot worse than the sensitivity at in what we call the bucket, and the signals are also going to get much weaker over there. So we'd have to do a lot of redesigning. So what informed this frequency dependent squeezing was what our science goals were now, and I think to some extent that was actually, let's try and do what we're doing, but better, find more binary black holes, learn about the population of binary black holes. So we are doing better. There's many ways to quantify it. The way I'd like to quantify it is saying that our event detection rate has gone up by 50 to 70%, I think.
So maybe I can give a direct answer to why Drew hasn't spent time thinking about this. Because the connection between the sensitivity in amplitude and the distance just comes from general relativity. So unless GR is really completely wrong, there's a simple connection. If I lower the noise by a factor of 2, then I can see things twice as well. That's it. It's somewhat different than for stars, sort of more astrophysical sources that have some thermal stuff going on. The physics involved for these sources is quite simple. So if general relativity is not painfully wrong, then that connection is clear. One last question, or we call it good? I think we call it good because we're out of time. So let's give Drew another round of applause. Thank you, everybody, for coming. Thank you, Drew. This was wonderful. And we will transition now to the closed door session in which we sort of pick everybody out, and the committee will stay here and ask Drew a lot of hard questions.
Yeah.
And eventually he will emerge.
Thank you,
sweaty,
everyone online.
tired.
I'm going to go offline now. But, yeah.